What's up, Trig? This is Mr. Carlson, C-Squared Mathematics. Welcome back. This is now going to be Unit 3, Polar Coordinates and Vectors. So we are now finished with Unit 2, that dreadful unit, and now we can get into the easiest unit in trigonometry. The reason why it's the easiest unit in trigonometry because it's not as many formulas to remember. Of course, there's still formulas, but there's not as many, and it's not a lot of identities and creative thinking that more or less cannot necessarily be taught to you. It's very straightforward, this unit is, and it has a lot to do with graphs as well, at least this week. So polar coordinates and vectors. Vectors are going to be next week primarily, and then this week is just polar coordinates, polar equations. What are they? What do they look like? We're going to get into it. So bell work, I have a couple questions, about I think 4 actually, questions from the Unit 2 tests. Some of them are honors. Maybe at least one of them is honors. The other ones are regular. Feel free to watch those as many times as you want. So when you take the Unit 2 retake, you can be prepared. We're going to go through 7.A. This is the first part of a two-parter, 7.3. So 7.A today, polar coordinates, and then tomorrow we're going to do 7.B, polar equations. Okay? And then summary, of course, closure, and so forth. So I have 4 questions here. These are the questions that I'm interested in going through. If you want to pause the screen right now, take a picture, whatever, then go for it, write them down. But these are the questions that were mostly missed on the test. And so I'd rather go through them, but I am going to go through them very quickly, especially these equations here. Okay? This third one is an honors question, and then the last one I believe everyone had. All right, let's get started. I'm so excited. This one is an equation. As I said, it is a trigonometric equation. But now, pay very close attention. We want to find the general formula. Now, most of you got the general formula correct, as in, like, you know that it has to do with plus 2 pi n. But a lot of you just did not give me the right angle, which is concerning because that's like the beef of the question. Okay, now because they didn't give us an interval, they just want a general formula. We do need to do the plus 2 pi n, or if it was tangent, the plus pi n. So since it's sine, it's going to be plus 2 pi n. So let's get started. I need to solve for sine of x. How do I solve for that? I simply subtract the 1 over, divide by 2. So I have sine of x equals -1 all over 2. This means x equals, I'm going to be looking on my unit circle or my trig table of common elements. Remember, this is what the trig table of common elements looks like. Okay? This is what the unit circle looks like. All right? Both on Google Classroom, just in case you didn't know that or you forgot. You should probably know that because it's very, very important. I'm going to look, where does sine, my y coordinate on the unit circle, equals -1/2. Okay, there should be 2 spots, and the first spot is 7 pi all over 6. Okay, and then the second spot is 11 pi all over 6. Now remember, because they want the general formula, I do need to add this plus 2 pi n, the plus 2 pi n. Okay, and that is my final answer. So a lot of you, like I said, got the 2 pi n correct, but you did not give me the right angle measure, or maybe you forgot just the n part and you just said plus 2 pi. The problem with this is you need the infinite amount of solutions. There is an infinite amount, especially if they don't restrict it to the unit circle 0 to 2 pi like you usually see. If they don't restrict that, that means they want all the solutions, hence the word all, okay? And that's just impossible because it goes on forever and ever and ever. The domain is negative infinity to positive infinity, which means you need to account for all those infinities. So you have to put in the n just in case, okay, for whatever x value you want to put in there. Okay, so that was the first one. Let's go through the second one. This one can be a little bit tricky, but once we know that we need to use an identity, then we should be solid. Now, this is going to be using the Pythagorean identity because right here, if I take sine squared x plus cosine squared x equals 1, and I actually subtract cosine squared x over, I get this. And this is the same exact Pythagorean identity, just a little bit manipulated, but that's okay because that's what we want, yes? So I'm going to be using this 1 minus cosine squared theta, or cosine squared x, and putting it in for sine squared x. So now I have 2 times 1 minus cosine squared x, and then minus cosine x minus 1 equals 0. What this means is when I FOIL this out, I get 2 minus 2 cosine squared x minus cosine x minus 1. I can start combining like terms here, so I will. So those can combine. And I have this, negative 2 cosine squared x minus cosine x. And then this is going to be plus 1. Now the problem with this is I don't want a negative out front with my squared term, so I'm actually going to divide by a negative 1 to everything, and what I do to one side I must do to the other, but it doesn't matter because it's just 0 divided by anything is still 0. So that means I have 2 cosine squared x plus, because I'm dividing that by a negative, so every sign changes, cosine x and then minus 1 equals 0. Now I can actually solve this quadratic by either plugging into Desmos, or what I can do is just straight up solve it by hand. I'm going to solve it by hand. So how I do this is the divide inside question, or strategy rather. So that is 2 times negative 1. This gives me negative 2. Factors of negative 2 that somehow, some way add up to a positive 1. Well, that's going to be 2 and 1 because those are the only factors of 2. Which one gets negative? The negative 1. 2 minus 1 gives me positive 1. 2 times negative 1 gives me a negative 2, which is what I want here. So now I'm going to do my basic template. And it does not matter where you put the 2 and the negative 1. You can put them right here. But the problem is I still need to divide by my leading coefficient. So I divide by 2. I divide by 2. That goes poofy, so I'm left with cosine of x in my first equation. Cosine of x plus 1 equals 0. My second equation, I have cosine of x minus 1/2 equals 0. So that means I have cosine of x equals negative 1. And in this one, I have cosine of x equals positive 1/2. When I separate everything and solve for cosine, that's what I want. That's the variable. So what is this? Well, I have to do my inverse operations here. So what's the value, the angle measure of cosine that somehow gives me negative 1 on the unit circle? And there's only really one of them, and it's pi. Technically, it's 2 of them, but remember, with 2 pi, it cannot, scratch that. I'm thinking of sine. Never mind. It is just pi. Just pi gives me negative 1. Perfect. Okay. I'm thinking of sine there. What about this one? This one, there's a couple more values here, and this is pi all over 3, and then 5 pi all over 3. And those are my 3 answers. 1, 2, 3. Remember, I am going to be on the unit circle, so that is the 0 to 2 pi there. So that is why all I have to do is just use my unit circle, or my lovely trig table of common elements. Angles. Man, I always say trig table of common elements because the periodic element table. Oh, that dreadful science. All right, this is an honors question, so you don't need to, if you're just regulars, you don't necessarily need to watch this, but it is a pretty cool question. There's an easy way and a hard way to do this question. The easy way I'm only going to show you for the sake of time, but, and it's actually rather intuitive. The hard way, though, is very, very satisfying indeed. So the first thing I want to notice is the way this is set up. I have cosine of alpha and a cosine of something else, and then I have sine of alpha and sine of something else. This expression, the way that it's set up here, looks awfully like an identity. It actually looks like a difference identity, and that's the point. That's what I want to try to get at. It's actually the cosine identity, okay, the cosine difference formula, okay, because what I could say instead is cosine of alpha times times cosine times cosine of beta plus sine of alpha times sine of beta. So that's what it actually looks like. It's just that it's not just a single beta, it's an alpha plus beta. But does it matter? No, because it's in parentheses. So watch, what I'm going to do is I'm going to say my alpha in my normal straight up cosine difference formula is alpha as well. Like that doesn't change. The alphas stay the same, right? Even with the sine function here and cosine function. But my alpha plus beta here will actually be equal to my beta, okay? So what does this mean? This means when I solve this, guys, I'm going to be looking at this stuff right here because that is from my formula. But this is from this formula. And what does that equal? That equals cosine of alpha minus beta. So I'm going to actually be using this formula right here and kind of switch out the alpha minus beta here. What am I going to switch it out to? These. So I'm going to switch them out to those. So now this is equal to cosine. My alpha is alpha, but my beta here, my beta minus my beta is alpha plus beta. So I need to put that in parentheses as well, alpha plus beta. So I have something like that, yes? So notice how I'm just replacing beta here, my normal straight up difference formula for cosine with alpha plus beta in parentheses. Now, how do I solve this? I have to distribute that negative, so I have minus alpha and then minus beta. But the problem is, after I simplify this, the alphas, which is great, right? This is awesome. After I simplify this, I have cosine of minus beta. Now, that doesn't really seem like an actual answer. And in fact, it really isn't. And we have to notice one more identity. This identity is what we call the even identity. What happens when you have a negative inside of the angle with cosine? Since cosine is an even function, what happens is it actually just goes poofy. Okay, just like an even function, if I take negative x and then square that, what do I get? Just a straight up positive x. I just get a regular or straight up positive x squared. I just get the same function back without the negative. Same thing here. I get the same function back, cosine of beta, without the negative. That's my final answer. Okay, so that is probably the easiest way to do it. I think Math Excel may solve it differently. I don't even think they have a viewing example on this one. But I really like that question. It's really great. So feel free to write that down and use it on your retake if you need to. Let's move on and let's go to our final and last question. It is a bearing question. So we're going to be asked basically how far apart these two ships will be. So two ships leave a harbor at the same time. One ship travels on a bearing south 14 degrees at 11 miles per hour. Another ship travels on a bearing north 75 degrees east at 10 miles per hour. So the first thing that I notice is this. I have north and then south. Okay. The first ship goes from southwest, so about somewhere southwest, like 14 degrees. So this I know is going to be roughly 14 degrees. Okay, because this is southwest, right? This is west, and this right here is east. Yes? So 14 degrees. Now, this right here, let me say, is 11 miles per hour. So the ship is going 11 miles per hour. Now, what does that mean? Well, we can't put 11 miles per hour on a freaking side length. So we have to read the problem very carefully, and we notice that these are correlated. After 2 hours, how far will the ships be apart? Before we get to the other ship, think about it, and this is what we need to do. I need to transfer this 11 miles per hour, if I can do abbreviations here, 11 miles per hour, and I need to multiply that by 2 hours. The hours go poofy, and now I get miles, which is what I want. So that means this is 22 miles. So this right here is 22 miles there. Okay? And so now we read the other question, or the other statement. The other ship travels on a north 75 degrees east. So north 75 degrees east. So it's roughly like, let me kind of get a better one right there. It's going to look something like this. It's not perfect, of course. Okay, I'm just kind of briefly drawing it. This is north 75 degrees east. And it travels 10 miles per hour. So let's go over here. 10 miles per 1 hour times a total of 2 hours. How far will the ships be after 2 hours? So they both travel 2 hours because they leave at the same time. That goes poofy, and this becomes 20 miles. So that means this right here is 20 miles. Okay? And this is also 22 miles. So now, what are we being asked to find? We're being asked to find what's in purple. How far apart will the two ships be after 2 hours? So I want to know what purple is. So I'm just going to label it. It doesn't really matter how you label it. I'm going to label this C, this A, and then this is B. It does not matter because the formulas will work no matter what. And so really what I want to try to find is C. How far apart will they be? So that means this is B equals, and this, of course, will be A equals over here. So far, so good. Now, the thing that I need to find is what is this total amount of degrees? That's what I need to find. What is the total amount for this degrees here? Okay, and let's put that in bright green. I need to find at least one of these angles in here. I don't care if I know what the angle A is or what angle B is. Let's try to find angle C. That's the most important angle, right? So how do I do that? Well, I know that this is 14, this is 75, so what is that? If that's 75, that must be 15, right? Because that means that's going to be 90 degrees. So, and then this is another 90 degrees right here where my cursor is a little at, like right here. So really what I'm taking is, what is angle C? So angle C equals 14 degrees plus 90 degrees from quadrant 4, and then plus another 15 degrees. Altogether, this should equal 119 degrees. That is what C equals. So that means this whole thing right here, what I'm doing in green, is 119 degrees. Okay? So since it's 119 degrees, I'm going to use that information to start solving for my question. How can I start solving for my question? Well, this is the third step. What are we actually going to be solving for? This, and how can I solve it? Well, in order to figure out how you can solve it, you need to know what you've been given. I have an SAS. So I have a triangle that is SAS, which means this is going to be the law of cosines. It's definitely not a right triangle, right? It's definitely not a right triangle because that degree is 119. So it's definitely obtuse, which means it's the law of cosines or sines, but then I see it's side angle side, so SAS, which means law of cosines. Now, if I want to know C, I'm going to be using this formula. C squared equals A squared plus B squared minus, and then I have 2AB, and then times cosine of C. Okay, so I know a lot of you probably created the SAS calculators and everything. I'm not going to show that to you on Desmos. I'm just going to do it straight up by hand. You start solving this as such. I'm going to do a full square root. So now I have A, which is 20 squared, plus 22 squared for B, minus 2 times 20 times 22, and then times cosine of C, which is 119 degrees. Okay, after I solve this out, it is roughly 36.2 miles. And again, I can just plug that in the TI-84 or the TI-36X Pro, or I can plug in the Desmos. Okay, that was a question that a lot of you missed, but I hope it kind of summarizes everything and how to actually solve it. Okay, I'm going to erase it now, and let's get finally started on the bell work. Finally get started on the objective and essential question, not the bell work. We just finished the bell work. How do I solve using polar coordinates. What is the polar coordinate system? How can I use it? Why should I use it? And how does it relate between the rectangular coordinate system, the coordinate system that we're so used to always? Okay, so we're going to be using a lot of stuff here. We're going to be doing conversions. We're going to be finding multiple representations, and we're going to be plotting coordinates. That's all we're going to be doing, those three things. So let's get started on plotting the rectangular and polar coordinates and how they differ. We already know how to plot rectangular coordinates, or at least you should. Rectangular coordinates is what I mean by that is the XY plane or the Cartesian plane from René Descartes. He's the one who created it in the 1500s. Okay, so, or in the in the 1500s. So, how do I plot these? Well, it should be very simple. Okay, so 1, 2 is all the way up here, of course. 3, -2 is down here. And then -1, 4 is up here. Very, very simple. You guys remember learning this when you're like in 7th grade, 6th grade, or something like that? Probably 7th grade. Very simple indeed. Or maybe even 6th grade for some of you because you're so advanced in math. I don't know. Okay, so that is how to plot rectangular coordinates. Now, how do I plot polar coordinates? Instead of using what we call XY, we're now going to be using what we call R theta. Okay, R theta. And so it's a little bit trigonometric instead of just algebraic, but it's very algebraic still, and I'm going to show you what that is. So this is what the polar coordinate system looks like. And as you kind of look around and see these little values, you're like, what the junk? That's just straight up the unit circle. Yeah, it's straight up the unit circle. Now, of course, there's some other values added here, like 5 pi over 12 for 75 degrees and 15 degrees. So there's some other values that are added there, but yes, it is the unit circle at its bare minimum, okay? And actually, you can find this out on Desmos. You can do this on Desmos. I'm not going to be utilizing Desmos really that much during this lesson because it's just not needed, to be honest with you. It's way simpler to not use Desmos. But I will show you that you can, in fact, actually get a polar coordinate system on Desmos. So this is your basic graph. All you have to do is go to settings and then just click on that for the grid. And then it automatically gives you your polar graph here. Okay. I would highly encourage you if we are going to be doing this a little bit later this week, and we are going to be using this graph and typing graphs in during a Desmos activity as well. But for the next couple of days, we probably won't be using this. But I encourage you to at least play around with this, type some certain stuff in, and just go with the flow, okay? To get familiarized, to get acclimated and familiarized with it, okay? So how do I actually plot polar coordinates, though? Is it very similar? Well, yes and no. It is very similar, but there's a couple nuances. So I want you guys to write this definition down, and then I'm going to explain it as such. So the sign R and the point's location in polar coordinates is really what this is saying. So the point P equals R theta, that's what we want for polar coordinates, is located the absolute value of units from the pole. That means it can never be like a negative distance. So these are never a negative distance technically. Now you will get negative R's, yes, but technically the distance is always going to be positive. Of course, right? Distance is always positive, so the R is always positive. Makes sense. So now, if R is greater than 0, what does that mean? That means it's positive. Okay, if your R is positive here, then the point lies on the terminal side of theta. What does that mean? I'm going to show you in a couple examples, but basically it's the easiest to plot. All you have to do is find your theta and then find your R value. Okay, if R is less than 0, if R is less than 0, not greater than 0, that means it's negative, of course, and then that means that the point lies along the ray opposite. So the ray, remember a ray is like this, like almost, this is technically a vector, and we're going to explain that more next week, but that's what like a ray looks like. It's going to lie on the ray opposite of the terminal side of theta. So if my terminal side was this, let's just say, that's my ray, the ray opposite of that is this. Okay, so I basically take it and I flip it over. That's the ray opposite, all right? So I hope that makes sense. And then if R equals 0, then the point just lies on the pole, at the pole, regardless of the value. Now, what is the pole? We're going to explain more about that in the next coming days. You don't necessarily need to worry about that. But instead of just an x-y axis, what we have is poles. Okay, that's why it's called the polar graph. It's actually heavily used, and maybe some of you may be thinking this already. Doesn't this look like longitude and latitude? Yes, it is. It's basically your globe is really what it is. It's basically, if you look at a globe, you see a lot of these kind of lines here, and you never really understood what they were, but they kind of drape along the globe like that, like almost like spider webs. But they're called the latitude lines or the longitude lines, and that's polar coordinates. Okay, those are polar coordinates, and that's why it's really interesting. We're mainly going to be focusing with r greater than 0 and r is less than 0. Now, before I get to the next slide, and so we can go through a couple examples, I want to explain one thing. So these are obviously my thetas. My thetas are on the outside all around, right? Those are all my thetas, my degrees, my radians. What's my r's? My r's are these little lines. So that is technically r equals 1. This would technically be r equals 3. This right here would technically be r equals, if that's 3, 4, 5, this is r equals 6. Okay, so I hope that kind of makes sense. It's basically how far you are from the origin. That's what your r is. Okay, so if my r goes all the way up here, okay, that means my r equals 6, and it's on a theta measure of 150. So if I wanted to plot that point here, this big fat point, that is technically r comma theta, which in this case would be 6 and then 150 degrees. That's the brief overview on how to plot polar coordinates. But let's actually get to some specific examples, shall we? So let's go through these 3 examples. And here are the steps. You're going to start by plotting your angle theta. That's always the first thing. You need to find where your angle is. And then you're going to start by plotting the distance r. So let's kind of focus on this a little bit and go to town. So 2, let's do this one in purple, 2 and then 135. So I'm going to go to 135. So 135 is roughly right here. Okay, so I'm going to kind of just recognize that that's 135. And what I'm going to do now is going to plot my r. So that's going to go up 2. Now, for the sake of clarity, I'm actually going to make this 1, and this will be 2. So I'm going to go by, and this will be 3. So I'm going to go by halves. Okay, so just so that I can kind of scale it up a little bit. So I hope you're okay with that, which means this would be down here, that would be -1. But I guess I don't need to write that. It's fine. So that means I want 2 135. So 2 135, it's going to be right here. Now, what this actually looks like, guys, is this. What you're going to be doing is you're going to be kind of traced along this value. Okay, so you're basically your initial side is this. I'm going to erase this so we have a little bit more. I'm going to erase this soon so we have a little bit more time, room to work. That's my initial side, and this right here is what we call your terminal side. Remember, that's your ending side from literally the first day of trig, right? That's your ending side. Okay, so this is your ending side right there, and that's your terminal side. Ending side, terminal side, because you start on the positive x-axis and go. So that right there is 135. That's 2 135. So let me plot that again. This will be 1, and this will be 2. So that means 2 135 is roughly right there. Perfect. Okay, so that is 2 135. Actually, let's label this 2 just in case. Now let's go to the red. So now it's negative 3 pi over 2. So where is 3 pi over 2? Well, 3 pi over 2 is all the way down here. And so basically what I'm doing is I'm going all the way around. So I'm right here. And now I want to plot my distance, which is 3. So 3 would be, that's 1, right? This is 2. And so 3 would be right here. So technically it would be right here. But the problem is, since it's negative, I go to the opposite ray. So the opposite ray, and 3 would be right here. Okay, so that means I'm going to plot the point right there, and that is negative 3 pi all over 2. So it's a little bit confusing. I get that. Okay, it's definitely different than XY planes for sure, but that's really the only nuanced thing. If it's a negative r, you do have to flip it. The other nuanced thing is this right here, when I have a negative r and a negative theta. Now, if you have a negative theta, guys, remember, you're just going to go down. So negative 45 degrees. So negative 45 degrees is right here. Yeah, 7 pi over 4. That doesn't change. However, it is a negative 1. And if this one right here, this circle that I'm kind of highlighting with my little pen here is 1, that means I go to the opposite side. Okay, roughly right here. Boom. I go to the opposite side. That right there, that point, that is negative 1, negative pi over 4. So you always start with plotting the angle first and then the distance r. Okay? Not too terrible, because a lot of your homework is going to be just plotting those points, which is great, right? Now, you could honestly, I guess you could technically plot these to 135. If I wanted to change this to degrees, I'm pretty sure it does plot it. So I can type in the point 2 and then 135 and plot it. I don't know if it actually does change it. Yeah, it doesn't. So this is one thing that Desmos is actually not good for, polar coordinates. It really doesn't, it just does not give you adequate polar coordinates. Even if, and that's the thing, even if you put it in degrees. It's like it should show up, right? But it doesn't. And that's the really unfortunate part. So this is really, I guess Desmos is only really good for graphing, which again, we're not going to do today. We're going to do in the next couple days. Okay, so representations. Now this is the hardest part of this lesson, is this little section right here, the representation. So pay very close attention. In rectangular coordinates, each point x, y only has one representation, meaning 2, negative 1, that's the only spot where it gets 2, negative 1. There's no other point that can give me the point 2, negative 1. Okay, so the point 2, negative 1 is unique to its position. However, in polar coordinates, that's not the case. Okay, we can have multiple representations because we can go round and around and around. We can flip back and forth with opposite rays, just like with negative r values and so forth. We can perform many different representations involved with this. And oftentimes, you're going to be asked to find 3 other representations. Okay, there is technically an infinite amount of representations. So think like coterminal angles. When we learned that in the first week of class, the coterminal angles, there was technically an infinite amount, but most of the time they only ask you like to find 2. So add 2 pi or subtract 2 pi and you got it. In a similar way, that's what we're going to be doing here. We're going to be kind of adding and subtracting pi or 2 pi. So in the first case, I can add 2 pi to the angle, and then I do not change r if that happens. Okay, so I can add 2 pi over the angle and do not change r. The second case, I can add or subtract pi, and this one's a little bit iffy because it depends on where the angle measure is. Pi to the angle, and then replace r with negative r. Okay, and then subtract 2 pi from the angle is my third case, my third representation from the angle, and do not change r. Now, how do I apply these? It's not like you're going to be given an example, like multiple points, and then you're just going to be finding all of these, like A, B, and C. You're only going to be given one point, one coordinate point for polar coordinates, and then you're going to be finding 3 representations, and those 3 representations relate to A, B, and C here. Now, the correct question you should be asking is, how do I know when to apply each one? Great question. I'm going to show that to you because it does depend on the interval that they give the point to you. Most of the time, it's just going to be between 0 and 2 pi, obviously the unit circle, and that's completely fine. But that's why I'm saying most of the time it does involve that. It depends on the interval, okay? And it also depends on the angle that you've been given. So the multiple representations of these points, essentially what you're going to be doing is this. This is like the formal way of writing it, essentially just plus 2 pi n here, or plus pi and then plus 2 pi n. I mean, that's one way to do it right here. I don't like this way. This is just a textbook way. I put that there just in case those of you who like to learn that way. But don't worry too much about that. Just get down the A, B, and C part, and then we'll move on. So I'm given this on Math Excel. I want to find the 3 representations. Now notice on Math Excel, they're giving you something like this. What they're going to be given, okay, is your angle measures, or your intervals. So 2 pi to 4 pi, 0 to 2 pi for B, and then negative 2 pi to 0. So they give you those intervals. Okay, just to let you know that these are also written like this oftentimes on Math Excel. So this is often written as 2 pi, comma 4 pi. This is often written as 0 to 2 pi in parentheses. And this, of course, is often written as negative 2 pi to 0. Notice how I'm not using any brackets here. That's just how it's commonly written. I want to find different representations of this point, 2 pi over 3. So let's actually plot that point right now. So 2 pi over 3. Well, pi over 3 is right here, which is really, really great. And then let's just say that this is 1 again, and let's just say this is 2. So pi over 3 is going to be right here, and that's 2. So that is my point. So pi over 3, and it's in my circle of radius 2. Okay. So that's really what it is. And if you wanted to actually write out like the terminal and the initial side, that's fine. But that's basically how you get to it. Doesn't matter. Okay. Actually, I want to do this. I say it doesn't matter, but then I'm actually like spending time on it. Isn't that cute? Okay. Looks a lot fancier, right? Perfect. So I'm going to keep it with that. Now that's my actual point. I want to find representations of this point. So how many times can I actually get the same point back? So let's go through A first. Now for A, what I'm going to do here is I'm going to actually add 2 pi here, and then not change R. So I'm actually going to write that out. So I'm actually not going to change R. Now, why am I going to do it this one? Now, if you remember, that one is going to be correlating to A. So it's not just because this is A and that was A. That's not the case. Okay, so I'm going to say that again. In the last slide, it was ABC. So you're not necessarily just going to say, oh, that's A, so I'm going to add 2 pi to it. No, it depends on the interval. Okay, so you may do on the last slide, you may on A, depending on the interval, you could subtract pi, or you could subtract 2 pi. It depends on what they want as the interval. Now, it just so happens that this A, between this interval, 2 pi to 4 pi, where R is positive, lines up with the A of the previous slide. Okay, it just so happened to be like that. But on Math Excel, I'm warning you, it's not always like that. Okay, so you have to pay attention to the interval. Now, the reason why I do 2 pi here is because of this interval. It goes from 2 pi to 4 pi. So that means if it goes from 2 pi to 4 pi, I need to make sure to go well past 2 pi. Okay, this angle measure, the initial angle measure that I'm given, is already within 2 pi. If I want to go past 2 pi, what I need to do is add 2 pi, right? I need to add 2 pi. Now, if I add 2 pi, that means I'm not going to change the R. That's the only one out of my ABC from the last slide that I could use. So I'm not going to change r. So what will this look like? Well, I'm going to take it like this, 2. My r is going to not change. It's going to chill, 2. And I'm going to take pi over 3 and then plus 2 pi. What this equals is 2, comma, pi all over 3 plus 6 pi all over 3. So I can add them up. And that equals 2, comma, 7 pi all over 3. So this is my first representation. Why? What is that? Why does that matter? Because what this says, guys, is that I actually go around the whole way. Follow my cursor, follow my cursor. I go around the whole way because 3 goes into 7 2 times plus, so it goes around 2 whole times, so 2 pi, plus an additional pi all over 3. So I get back this point again. That's what I'm saying. I get this point back. All right? And so that's the representation. So now let's go to B here. R is negative. So R is negative, which means I'm going to obviously change R to negative R. Okay? But then what am I going to do? Am I going to add 2 pi or am I going to subtract 2 pi? Well, if I subtract 2 pi from pi over 3, that means I go into the negative angles, yes? Because pi over 3 is just right up at the top. Okay, if I subtracted pi, it would go into the negative angles. And that would not be within my interval, 0 to 2 pi. So that means I need right here to add just pi, add pi because I need to be within another representation within the unit circle. So add pi, but then that also means I'm going to change my positive r to a negative r so that it looks like as follows. Ready? So I have a positive r to a negative r, so I'm going to do negative 2 now. And then this is going to be pi all over 3 and then plus pi. This becomes negative 2 pi all over 3 and then plus 3 pi all over 3. I know it's really small there. I apologize. And so what is my actual coordinate point? Negative 2, comma, and that will be 4 pi all over 3. So this right here is my actual coordinate point. What is that? Well, 4 pi over 3, watch. If I do 4 pi over 3, it's right here. Yes, that's 4 pi over 3. And then the 2 is roughly right here. Okay, so it would be right there. But since it's a negative r, what happens is it goes on the opposite ray, which gives me the point back. Okay, so it's a multiple representation. Make sense? So it's very similar to coterminal angles in that regard. Okay, so now let's continue to our last one, C. So let's do this one in purple now. So C, R is positive. So that means obviously I'm not going to change R, right? Because it's already positive. Now I want in the negative angle measures, radian measures, which means I'm going to subtract. So subtract pi or 2 pi. And I'm going to keep R the same. So subtract 2 pi and I'm going to keep R the same. What does this equal? Well, I'm going to keep R the same. I'm going to have pi over 3 minus 2 pi. So this equals 2 because the r is the same. And then this is comma pi over 3 minus 6 pi all over 3. And this will actually equal 2 comma, this will be negative 5 pi all over 3. Now, if I do negative 5 pi over 3, what it would technically do, guys, is this. I would go the negative route, 5 pi over 3, which would give me right here. And then since it's 2 and not negative, I just plot the point. And again, once again, it's the representation. Okay? Awesome. So that is the representations. I'm going to give you another example, but I want you to try to do it yourself. So I'm just going to pop up the the work on the screen. So let's move on. I know that one took a long time. Let's go through this one. See if you can do this by yourself and see if you can get the actual right answers after you go through it. So go ahead, pause the screen, try it yourself, see if you can kind of get to what these representation points are, and then see if you can plot it. Okay, welcome back. This is my actual point in green, 5 comma pi over 4, so it's chilling right there, and these are all the representations. So which one represents which one? Well, this one I have to keep r the same and then add 2 pi because I want that 2 pi to 4 pi. So keep r the same, add 2 pi, I get that representation when I do the math. And then this one I'm going to actually change the r to a negative because that's what it says. But then I'm also going to add pi so I can still get that representation. So the r is flipped, but then if I add pi, I still get to the same point. That's what I have. And then right here, I just subtract 2 pi because r is positive. I just keep it the same. I subtract 2 pi, okay? And I get this. So if you got that correct, awesome. If not, that's okay. Continue going through the work on Math Excel and hopefully you'll be able to get it. If not, just email me. Let's move on to our last couple of examples. Our last topic that we're going to be going through, how to convert between polar to rectangular. How to convert between polar to rectangular. We're going to go through at least 2 examples here, and then I'll show you how to do rectangular to polar, just like degrees to radians, radians and degrees. Similar, polar to rectangular, rectangular to polar. And I'm going to show you a couple examples there, and then I'm going to show you how to do it on the TI-36X Pro. So to convert between rectangular and polar coordinates, we will use familiar trig functions and equations. What are those familiar trig functions and equations? Well, look at these. We're going to be using a lot of these. So right here, these two I'm only going to be using for polar to rectangular. Now these, I'm going to show you where I get these and how I derive them. Just give me 1 second. But right here, we're only going to be using these towards polar to rectangular. So I only use these equations when I want polar to rectangular. And we are going to be doing that in the next slide. So I'm going to be using those 2 equations, x equals r cosine theta, y equals r sine theta. Now, on the opposite end, though, I'm going to be using these equations for going to rectangular to polar. And that's going to be my last couple examples there, okay? All right, so now how can I get, in blue, how can I get these 2 equations? Well, think about it. Given this rectangular coordinate, I guess, sure, but triangle. Given the triangle, it's something that we actually did before we built the unit circle, way back when. We got this triangle, okay? Now, we said that this was x and that was y, and that was theta. This is r, my distance, right? Yes, that's what we said. Fantastic. So, think, what did we say cosine of theta was? What did we say for the first one, cosine of theta equals? Well, that's adjacent all over hypotenuse, Mr. Carlson. Great job, kids. What's my adjacent? X. What's my hypotenuse? R. What if I wanted to solve for x here? Just times r, which means this gives me r times cosine of theta equals x, which is exactly what we have here. Okay, that's how I derive it. Now, if I wanted the second one, okay, what is sine of theta? Well, that's going to be y all over r, using my triangle here, y opposite all over r, hypotenuse, times r, that goes poofy, so that becomes r times sine of theta equals y. And this, of course, is exactly what I'm given here. So they can be derived using that way, and we're going to be using these formulas in the next example. So this is what the textbook says, something that you don't necessarily need to write down as long as you have everything else. It just says we're going to be using those formulas, and I already told you that right here. Okay, let's move on and let's go to the examples. These are actually very simple, just because it's kind of plug and chug a little bit. So I'm given these 2 polar coordinates, and I want to go from polar to rectangular now. So find the rectangular coordinates of the 2 points. Let's go to town. So I first have to realize that this is r, and then this is also theta, okay? So that means I'm going to be first finding 2 different things. I'm going to have first finding my x-coordinate, which is r times cosine of theta. And then my second thing that I want to try to find is the second part where I have y equals r times sine of theta. After I do that, I'm going to go to my third part to actually label what my x, y point is. Okay, so I'm trying to find x and y given my polar coordinates. So what's my r value here? My r value is 2 times cosine of 3 pi all over 2. Now, since this is actually rather straightforward, all we need to do is look at cosine of 3 pi over 2 on the unit circle, and I should get 0, which means 2 times 0 is just straight up 0, which means x is 0. So that's my first coordinate here. Perfect. What I have here is going to be y equals, and then my r is 2, and then sine of 3 pi all over 2. Now, sine of 3 pi over 2 is actually negative 1, so that means it's going to be negative 2, because negative 1 times negative 1 times 2 is just negative 2. So that means this is my coordinate point. The smiley face is where my actual answer lies. That is my point. Okay? Not too terrible, right? Very straightforward. Straight up, simple. So now here, let's try to have this one done by yourself. Try to pause the video, see if you can do the next one by yourself. Here are the formulas for you. So I have r times cosine. I need to find cosine theta. I need to find my x first. And then my second part, I need to find my y. So r times sine of theta. Go ahead, see what you can get. Pause the video. Boom. These are my answers. So this is my x-coordinate, negative 4, my y-coordinate, negative 4, radical 3, and then I put them together, and this is my final answer in xy rectangular coordinate form. Okay? Sweet. Let's go into rectangular. That was polar to rectangular. Now let's go to rectangular to polar. So let's erase this. Let's go to rectangular to polar. These are my steps, rectangular to polar. Remember, I'm using two different formulas here, the ones I highlighted in 2 slides ago. In slide 13, I'm going to be using this one. Now, this right here is just the Pythagorean theorem. Okay, it's when it says calculate the distance, all they're saying is the Pythagorean theorem. Okay, so this was x squared plus y squared equals r squared. It's literally just a circle Pythagorean theorem distance formula. We already should know that, yeah? Okay, so now that's that. And then the other formula that I'm going to be using is the inverse of tangent. So the inverse of tangent. So make sure you have your TI-36X Pro or your Desmos calculator out so you can calculate that. But these are the steps. Write them down, pause the screen, and we're going to go through these steps very, very clearly. Good deal? Awesome. Let's go to town. This is when r is going to be greater than 0. If it's less than 0, then it doesn't necessarily work out, and most of the time you're not going to be converting when it's less than 0, because again, that would be a distance that's less than 0. All right. So I only have this question for us. Let's go to town on this. The first step that I want to do is actually build this triangle. So where does this point lie, actually? So this is negative 1, radical 3. So this lies in quadrant 2. So I'm actually going to build this triangle. We should be very familiar with building this triangle now. I don't really know what theta is, but I eventually will know what theta is. So this is, of course, negative 1, and this right here is radical 3, which means this has to be r must be 2. Now this is a special right triangle, but just in case we didn't know that, I will show you how to do it. You just use the Pythagorean theorem or this modified formula. Okay, so r equals radical, and this is going to be radical 3. Sorry, that's technically my y. I don't want to mess you guys up. Negative 1 squared plus, and then radical 3, and then squared. This gives me 1, and then plus 3, which is radical 4, which is 2. So r is 2. But again, this is a special right triangle, so we should have known that that was 2 all along. That was my third step. Or sorry, my second step. My third step is probably the most important step, your tangent. This is when I'm actually going to be using the inverse tangent here. Okay, inverse tangent. Now, the reason why you're using inverse tangent is because you're only given x and y. And tangent has x and y into it, right? So y all over x, which means you're going to be using the inverse of tangent of y all over x to equal your theta. Because really, I want to know what theta is, right? So that means, what does this look like? My theta equals the inverse of tangent. My y-coordinate was radical 3, and then my x-coordinate was negative 1. So when I plug this in, what I get is actually 2 pi all over 3. Now, if I plug this into Desmos, you would get probably a decimal, I think. Or if you change it to degrees, probably I would change it to degrees, do the inverse, and then give it to you. Or you can just see, okay, where on the trig table of common angles does tangent give me a negative radical 3? And it's just 2 pi all over 3. Okay, this is my theta, which means my fourth and final step, my r comma theta. What is that? That equals my r is 2 and then 2 pi all over 3. That is my theta. And this is how you go from rectangular coordinates to polar. Okay? Like I said, not too bad, right? Very, very simple indeed. Let's erase this and then go to, I have this question. Totally forgot this question. Pause the screen and see if you can do it. Let's do this as like a checkpoint. Pause the screen, see if you can do it. This one was a little bit tricky just because it had no real r, meaning it didn't have a triangle extending up. It does have an r. We can still go through x squared plus y squared, and it gives me 2. And then I can use those values, negative 2 is 0, my x and y, to find the inverse of tangent. I can just plug it in, and I get a degree in radians of 0. And so that means, boom, right here, that's my actual answer, 2, 0. And this is still technically r comma theta, even though it looks like a rectangular point. Okay, so now how to do on the calculator, I'm going to go through these really, really quick. So if you have the TI-36X Pro, and if you want to know how to do this on the calculator, it's actually very fascinating. If I want to go from polar to rectangular, I would go first, push math, then go to R and P, option 1 or 2, and then you would just follow the steps. Okay, you would first have to do this one to find your x coordinate, and then this one to find your y coordinate. Okay, that's what the Rx and the Ry is. You need to kind of plug them in. Make sure you're in proper mode first, like radians or something. If I want to go from rectangular to polar, I go to option 3 or 4, and then that would give me my rectangular to polar, first my R, and then down here at the bottom, rectangular to polar, and then my theta. Okay, again, make sure you're in the proper mode. Very intuitive. It doesn't always work, especially if you have like a radical for like an x value and a y value. It won't work. It'll give you a decimal, and then it's not really useful. You would have to solve it by hand anyways. But if that's not the case, you can always try it, and then sometimes it pops out a whole number. Then boom, you're done. You don't even need to do the math. Okay. So what do we learn? We learn how to plot the points. We learn how to find multiple representations, and we also learn how to convert between polar and rectangular coordinates, and then also briefly how to put it on the calculator. And I guess, yeah, from rectangular to polar. So retakes, Unit 2 tests available this week, of course. So make sure you are talking to me so that you can do the retake if you need to. This is C-squared mathematics, guys. Make sure you do the homework. Optional homework quiz tomorrow. But make good choices. Be sure to like and subscribe. Peace.